Good evening, everyone. Welcome to the week 11 live interaction session for the course Polymer Concepts, Properties, Uses, and their Sustainability. So, let's just wait for a few minutes for others to join before we start our session for today. So, let's start our session for today. So, let me just share my screen. I hope my presentation is visible and I am audible. Okay, so I welcome everyone to the week 11 live interaction session for the course Polymers, Concept, Properties, Uses and Sustainability. So this course is offered by Professor Abhijit Deshpande sir from the Department of Chemical Engineering IIT Madras, under the NPTEL program. Myself, Pratyumnan, a PhD research scholar from the Department of Chemical Engineering, Guwahati, is here for this live interaction session. So, till now, we have come across 10 10 live interaction session, and we are almost towards the end of the course. So, we have discussed a lot in detail about polymers, concept, properties, and uses. We have had a comprehensive discussion on almost all the perspectives of polymers. We have dealt with many concepts in detail, and many of the concepts as an overview. So in the last live interaction session, we were discussing more about the polymer processing and the recycling aspects in the last two live interaction session. So I hope you are able to recollect what we discussed. So in week 9, we discussed about polymer processing. So we discussed about the different strategies to process a polymer. One of the ways is through extrusion, which is the most commonly and widely used polymer processing operation. We discussed about its basics, and we discussed the key variables that affects the extrusion process, and also we discussed about something so called as injection molding. So in the last live interaction session, we continued our discussion on polymer processing operations. However, in the in that particular session, we discussed more about the operations that happen after the extrusion process. So something so called as post extrusion operations. So we discussed about shaping of these polymers, and after that we discussed on different types of post extrusion operations such as stretching, blowing, rolling. So I hope you are able to recollect all those things. And also we discussed in the shaping operations, one of the main thing that we discussed was why is the shape of the die and then the shape of the final extruded product are not the same, but they are a little bit different from one another. So as we discussed earlier also, it is due to the macromolecule property. So it's due to the property of the macromolecule in which they actually tend to stretch as well as recover back when they are forced through the die. So when they are forced through the opening, due to the just okay, due to the segmental stretching as well as the recovery, the polymers will tend to have a different shape. So if you have the, let's say for example, if you want to manufacture a cylindrical product, and if the die is also is in that shape, then what could happen is, because of this macromolecular stretching and the recovery, the shape of the material that you're going to get out, that is your final extruded product, may be different. So in order to make sure that you get that extruded product in the shape that what you intend for or what you have targeted for, the shape of the die has to be a little bit different because of this particular property. Then we discussed about blow molding, so that we discussed in detail with a flow diagram. So I hope everybody is able to recollect this one. Just a second. So this was, so this is about the blow molding. So a very common processing operations for producing the plastic water bottles that majority of us use. So this blow molding, as such, if you see, it can be categorized into 5 different steps. So the first step is basically the creation of the preform or the parison. So here the polymer that you are going to actually use is made into a cylindrical form, or you can say a hollow tube, which is called as a preform. This preform is placed inside the mold. Then inside this hollow tube or a hollow polymer tube, or basically you can say the preform, compressed air at high pressure is blown inside. Since the polymer can actually stretch, as I said, the macromolecules have segmental flexibility, and because of which they can also stretch, so the air inflates this parison or the preform, forcing the polymers to expand to the mold walls and coat on its surface. Once that process is done, the mold is cooled and solidified. Once cooled and solidified, the mold is open and then the finished product is ejected out. So this is a typical process for the manufacturing of plastic water bottles. And since this entire process happens very fast and quick, the time for producing this kind of for this blow molding process is very short. So this remains as one of the commercial advantages of producing the plastic water bottles using the blow molding process. Again, any process whatever we are going to use for our for manufacturing of any product in large quantities, that particular operation should be cheap and should be quick, so that those two are if usually remains as an important condition, because you don't want to take a lot of time for producing certain quantity which is actually required, or which is required in a large, the demand is more, and also it should be cheap so that it is not very expensive. Because if it is going to be too much expensive, then the demand of for the product may, then what can happen is people may not be willing to purchase because of the cost. It may not be economical for the purchase, so that has to be kept in mind when we go for manufacturing of plastic materials which are required for daily use, or which are used in daily, which are used by us daily. So that is about blow molding. And also we discussed about the recycling of the polymers, that is mainly towards their sustainability aspects. So over there we discussed quite a few types of recycling techniques, their classification. So we discussed what is primary recycling, secondary recycling, and how and what is the difference between primary recycling and secondary recycling, and what is downcycling and upcycling. And in case of upcycling, so downcycling is basically you're going to take the waste plastic and recycle them so that you can use it for certain applications with the lower performance requirement. However, in case of upcycling, what actually happens is you're going to take the waste plastic, recycle them, and then use or recycle them and modify them in such a way that you can use these plastics for higher performance requirements. So their application is going to be in a place where the performance metrics are going to be high. So that kind of recycling operation is called as upcycling. So in order to do that, in order to do the upcycling, you need to actually do some modifications, or you can say you have to come up with certain strategies so that you can enhance the property of the plastic or the polymer. So the two major ways for upcycling, or you can say enhancing the property of the recycled polymer, is through either use a filler or a reinforcement, or you can change the molar mass distribution of the polymer. So you can use some sort of a reinforcement or filler depending upon the type of applications where you want to use the recycled product for, or you can change the molar mass distribution by using certain operations wherein you can reduce or increase the chain length, which can help in changing the mass distribution of the polymer, or come up with new uh, different type of techniques or synthesis techniques so that you can change the molar mass distribution of a polymer. Apart from that, we also discussed about pre-cycling operations, which is like sorting and cleaning, and you can say reduce the volume of the plastics. We also discussed about the challenges that comes with the recycling of the plastic. One of the major problems is the processing of the plastic mixture. So since this plastic waste is going to have polymers of different varieties, so each of them may not have same temperature for processing. So one polymer may melt at a lower temperature compared to that of the other one. So this may result in the degradation of the polymers, and blending issues are also one of the important aspect in which is seen as a challenge in case of recycling of the plastic product. Again, within upcycling, there are also two types of other classification. One was mechanical upcycling and chemical upcycling. So again, in chemical, you do some sort of a functionalization, a chemical process to upcycle the product. In case of mechanical upcycling, you're going to resort to mechanical means to enhance the property of the recycled plastic waste which you are going to use for certain applications. So this is what we discussed in the last class. So I hope everybody is able to recollect. So coming to today's live interaction session or today's course content, it is typically going to be more on the concepts of polymers. It is a continuation of polymer processing and recycling, but here we will be discussing more on rheology of the polymer and their viscoelastic models, which is something to deal with when we go for polymer processing. And apart from that, we will also discuss about the concepts of swelling in case of the polymers. So when you talk about rheology, we also discussed this, I hope, in the previous live interaction sessions also. So rheology as such, it means that you are going to study the flow of a fluid under certain conditions. So based on this rheology, we define various models to quantify this rheology, or you can say we devise different models to understand how a particular fluid is going to flow under different conditions, or how a fluid will behave under different conditions. It can be a different strain conditions, or how the polymer is going to behave at different strain rate. So that is what we are interested to discuss in this session. So since it's about the rheology of the polymer, and as you know, polymer exhibits both viscous as well as elastic behavior, and that's what actually makes polymer a bit polymer complex when you try to discuss its flow behavior, because it's not going to exhibit only viscous behavior just like in case of the other liquids that you see, or it's not going to exhibit only elastic behavior just like in case of the solids. It's going to exhibit a combination of both. That's the reason we call polymers as viscoelastic materials, because it exhibits both viscous as well as elastic responses. So this so when we are as I said, since we are discussing about rheology and we need to see how this polymer systems behave, so we are going to come up with the models to see their behavior or to understand their behavior. So usually these models are classified based on the energy storage or the energy dissipation. So that is something like storage modulus and loss modulus. So as such, discussing about the viscous model, so these viscous models are something similar to that of the fluids that you see, the viscous fluids. So we use those models here as well, and then we try to understand how this model helps in understanding the rheology of the polymer systems. So as we talk about viscous fluids, the very first thing that comes into our mind, or the classification of the viscous fluids, is based on is is into two different categories. One is the Newtonian fluids and another one is the non-Newtonian fluids. So just let me write that. So in the viscous models, the very first thing is the Newtonian Newtonian and another one is your non-Newtonian fluids. So anyone, I think this classification we have discussed previously as well, and this is quite basic. So anyone who can define what are Newtonian and what are non-Newtonian fluids? Again, the very basic definition as we discuss this for viscous fluids. Newtonian fluids and non-Newtonian fluids. So usually these viscous models are kind of uh, usually this viscous model, what it actually conveys is that the state of stress is usually expressed as a function of the strain rate at that particular instant, right? So the stress is defined as a function of strain rate, or the stress is usually expressed as a function of strain rate. So that is for a viscous fluid. So in that viscous fluid, we have two categories of classification. The first one is your Newtonian, and the second one is going to be your non-Newtonian fluids. So in case of Newtonian fluid, they are going to obey the Newton's law of viscosity. In case of non-Newtonian, it is not. So it's not going to obey. So based on this, just tell me what do you mean. I mean, I just told, because the Newtonian fluids are the ones that obey the Newton's law of viscosity. So can anyone tell me how that is mathematically represented? Anyone? So, in case of the Newtonian fluid, they obey the Newton's law of viscosity, where your stress, or you can say shear stress, is going to be proportional, directly proportional to shear strain. Is directly proportional to shear strain. Shear strain rate. Or you can say that shear stress is going to be directly proportional to strain rate as well. That is acceptable, but in order to be very clear, shear stress is directly proportional to shear strain rate. Whereas in case of non-Newtonian fluids, this is not the case. Again, they are going to have a relationship. The shear stress is again is a function of strain rate. The shear stress is a function of strain rate, but that function will not be a linear one. That is the typical difference between the Newtonian and non-Newtonian fluids. The shear stress is directly proportional to shear strain rate in case of Newtonian. In case of Newtonian, again, the shear stress is going to be a function, or is going to depend upon the strain rate, but that dependency is not in linear fashion, is not going to be a linear model, unlike in case of the Newtonian fluids that we observe. So, just a second. So, based on this, since this function is not going to be a linear one, so non-Newtonian fluids itself can be described into two different types. So, anyone, again, we did solve a question related to those non-Newtonian fluids and then the type, their behavior. Anyone? We discussed about two types. So, one is the pseudoplastic and the other one is dilatant fluids. So any I mean, since I have, so since the names are now here, can anyone tell what do they actually mean? What does a what do you mean when you say a non-Newtonian fluid is going to exhibit pseudoplastic behavior, or what do you mean when a non-Newtonian fluid is going to be a dilatant fluid? So the directly proportional, over there the proportionality constant is going to be the viscosity of the fluid that you are taking under consideration. The constant is viscosity of the fluid. So pseudoplastic and dilatant. So in case of pseudoplastic, what happens is the viscosity of the fluid is going to decrease, or the viscosity of the fluid decreases with the increase in shear strain rate. So as you keep increasing your shear strain rate, the viscosity of the fluid is going to decrease. Whereas in case of the dilatant fluids, it is the it is exactly the opposite. So over there, the viscosity of the fluid increases with increase in shear strain rate. So this is the difference, or you can say this is the classification of non-Newtonian fluids. Apart from that, you also have something so called as a Bingham plastic. So anyone have any idea on what is Bingham plastic in case of so Bingham plastic is nothing but they are those kind of fluids which exhibit flow behavior only after a certain stress called yield stress. So any value of stress that you apply which lies below this yield stress, there will be no flow. So only when the stress that is applied on them exceeds the yield stress, they exhibit a flow behavior. So so the yield stress here is something more like a threshold value beyond which the fluid is going to exhibit flow. So can anyone make few guesses on what kind of fluids can exhibit this pseudoplastic behavior, dilatant behavior, and this Bingham plastic behavior? Behavior. I have now mentioned given what exactly each means. We have discussed this previously as well. So any kind of interpretation on what kind of fluids that you see in your real life can match with these definitions that we have listed here. Uh, any examples of anyone at least? I think dilatant will be quite easy, or you can say Bingham plastic is something that example what I'm going to, I mean, the classic example is something that you observe or encounter almost every day. I mean, you encounter every day that one. So, in case of, as I said, first let us think about the example of Bingham plastic. So, I said they exhibit flow behavior only when the applied shear stress is going to be greater than the yield stress. So, until certain stress you apply, they are not going to have any flow. Once that flow is greater, then there will be a flow of the fluid. So, can you think of something which, so the classic example for this kind of systems is nothing but it's going to be your toothpaste. So if you can visualize this, so till you apply a certain stress, the toothpaste will not come out of the tube. Only when a stress exceeding a particular value is applied, the paste actually comes out of the tube. Again, it's not just about only toothpaste, but any other kind that exhibits such kind of behavior, like let's say your um, face wash or anything that typically comes out of a tube only after you apply a kind of a stress, it's kind of a increased stress that goes par the yield stress value. Those kind of systems are usually termed as Bingham plastic. So next, let's come to dilatant. What could be the example? So when you increase the strain rate, the viscosity of the fluid is going to increase. That is, it is going to become thick. There is again a classic example for dilatant fluids. So the most common one, or as I said, classic example is cornstarch in water. So you take cornstarch and then you add them to the water. What usually happens is at low strain rate, they are not they are just going to disperse in the water. However, when you increase the shear strain rate, what actually happens is the cornstarch particles actually come together, and then they starts forming clusters of cornstarch particles. So because of which, since larger amount of particles are going to form as you keep on increasing the force that you apply onto the system or stir um, the speed, if you are going to keep on increasing with time, then what happens is many of these corn particles in the water are going to agglomerate, forming clusters, due to which the viscosity is going to increase. So this is the classic examples of a dilatant fluid. Now let's come to pseudoplastic. Think something more similar in a line, something very similar to dilatant one. So what about the example of paint? So once you keep increasing their shear strain rate, the viscosity of the fluid is going to decrease. That is, they are going to become more thinner and they exhibit a increased tendency to flow, unlike in case of the other materials. So paint is a classic example. Again, these are just a very few example, just one example in each category. there are multiple solutions, or you can say multiple material systems which typically exhibit this kind of flow. So coming back to our discussion, that is your polymer solutions. So polymer solutions are typically going to be non-Newtonian in nature. Polymer solutions are non-Newtonian in nature. So majority of the polymer solution, because of their high viscosity, again this we discussed before as well, why it is, why polymers exhibit non-Newtonian behavior. So in all these cases of pseudoplastic, dilatant and Bingham plastic, as you see, the viscosity is actually going to be a function of the shear strain rate. So they are not going to remain constant irrespective of what kind of strain rate is getting applied. As the strain rate is going to change, the viscosity of the fluids is also going to change in these cases. So, if you have to express this mathematically, then you can write it this way. Eta is going to be, just a second, let me, eta is going to be proportional to gamma whole power n minus 1. Actually, this has to be, just a second. So the viscosity is there going to be proportional to gamma dot whole power n minus 1. So gamma dot is nothing but it's going to be the shear strain rate. So gamma represents for shear strain, and since this strain is going to vary as a function of time, we usually represent that in the form of a dot on top of the variable. So this is going to be a standard. So this is a standard notation to express something that varies as a function of time. You usually represent that particular variable with the dot. So the whole power n minus 1. So here n, where n is nothing but it's called as the power law index. So this typically differentiates whether your fluid is going to be pseudoplastic or dilatant. So I hope you can make it out from here. So how, under what values of n your fluid system is going to be pseudoplastic, dilatant or Newtonian one. So what will happen if n equals to 1? So let me take this as only as an example before we progress further. What will be the value of n? If sorry, what will be, how will this relationship vary if, or how, what does this relationship actually convey to us if the value of power law index, that is n, is going to be 1? Or what will happen if n is going to be equal to 2? So if n is 1, 1 minus, so if you put it in the above relationship, the empirical one, viscosity is directly proportional to gamma dot whole power n minus 1. So if n equals 1, it means that viscosity is directly proportional. 1 minus 1 is going to be 0. So anything to the power 0 is going to be 1. So what it actually means is viscosity will not be a function of shear strain rate. So and in case of which type of fluids this happens? Viscosity is not going to vary. Newtonian fluids, so only there, if you see, the viscosity is a constant. They are not going to actually vary. So similarly, try to identify what will happen if the value of power law index is going to be less than 1 and greater than 1. So think about this. I hope you will be able to find out in which case power law index will be less than 1 and in which case power law index will be greater than 1. So this is about very basic introduction, very basics of these viscous fluids. Now we have to deal with certain specific viscous models. So the very first model that we are going to describe here is nothing but it is called as Carreau, Carreau, Carreau model. So this is the very first specific model that we are going to discuss right now. So it is called Carreau Yesadhau model. So here this typically explain to us about the shear thinning nature of viscosity in case of polymer melt. So this typically explain to us the shear thinning nature of the polymer melts. So this shear thinning typically happens at a higher or moderate shear rates. So anyone who knows how this particular relationship is defined, that is the equation. Anyone who knows the exact relationship? So just think about that. Before that I will write it for everyone. So let me put it in the form of equation itself. I'll try to write this ASAP. Meanwhile, if anyone knows, please tell me what is the equation so that it will be easy for me to write. Anyone who knows the equation? So this is the mathematical expression for the Carreau Yasadhau model. So here we have to discuss about certain parameters. So the first one is going to be your eta naught. So eta naught is nothing but it is eta naught is called as the zero shear viscosity. So what it actually means is the constant viscosity, that is a constant viscosity at zero shear stress. Similarly, apart from other than this, you have eta infinity, which is nothing but it is called as infinite shear viscosity. That means it is basically the viscosity of the fluid at high shear rates. Then you have lambda. So lambda is nothing but it is the time constant. Sorry. So this basically controls how quickly the fluid's viscosity transition from the zero shear plateau to the power law region. And you have n, which is again the power flow index, and you have the a. A also describes about how does the flow or fluid transitions from the zero shear stress to the power law region. So in this case, what you can actually, if you see all these kind of models that you have, they are usually derived from certain model, and then what is usually done is certain conditions are imposed on them, and then they are usually reduced to a simpler form. Again, this simpler form can be used only under special conditions because they do come with certain constraint. Like for example, from this model, another model was derived, which is called as the cross model. So that is called cross model. So what is a cross model is nothing but the high shear viscosity that you have is going to be 0 in this case. So eta infinity, if you substitute it as 0, so you can express this, excuse me, sorry, just a second. Yes, so so if you substitute the high shear viscosity or eta infinity as 0, then the model will be simplified, and that simplified model is called as the cross model. So if you rewrite this equation, then it will be something very similar. It will be something like this. So this is the cross model. So here you are just going to imply the condition that the viscosity of the fluid at the high shear rate is going to be 0. But under what condition does this happen, or when does this happen? That is, when does your viscosity of the fluid at a high shear rate is going to become 0? Because it should happen at certain conditions, right? I mean, of course, mathematically we do try to simplify this equation. However, that particular constraint that we are applying to that mathematical equation should actually have a physical meaning, or it should happen in a it should happen at a particular condition. So under what condition does this high shear viscosity of a system can become 0, or of a polymer systems becomes 0? Conditions. So think about this, in which condition, think in line with the polymer systems. So apart from this model, there is also another model called Herschel bulky model. So that also describes about the rheological property of the polymeric system. However, that is something related to the polymer system that usually contains fillers that gives them the network structure. So in those kind of polymer system, it's not just the polymers, or you can say the homopolymers. Oh, they actually contains fillers in them that give their network structure. So since a network structure is formed, the rheological behavior will vary distinctly. So as per Herschel bulky model, they exhibit something very similar to what we discussed about the Bingham plastic right now. So in those kind of in those model, so in that particular model, it is described that since the polymers actually form networks, so as you add nanofillers, the major reason why you do is that you have to form a network structure so that the crosslinks will be more in those cases. So because of the crosslinks being high, what happens is the flow in those kind of systems happens only after a certain stress, which is called as the yield stress. So until or unless the stress applied exceeds the value of the yield stress, there will be no flow. If the stress applied exceeds that of the yield stress, then there will be a constant flow, or you can say a steady flow with a particular strain rate. So that is what is the that's what the Herschel bulky model actually describes. So for any kind of a polymeric systems that contain nanofillers in them to form a network structure, because of the presence of the crosslinks, what usually happens is, for a very low stress that is applied, these crosslinks will not actually break. So because of that, there will not be any flow. This happens up to a certain stress, which is called as a yield stress. Once that applied stress exceeds the yield stress, there will be a steady flow in case of this polymer systems. So till then, there will be no flow, and then the polymer systems exhibits more of a solid like behavior. So these two models that we or you can say three models that we describe here, the Carreau yes thou model, the cross model, and then the Herschel bulky model. All these three models are something of you can say comes under the classification of the linear viscoelastic models. Again, when I described about the linear viscoelastic models, we even have encountered or discussed in detail about the Kelvin-Weigelt model and the Maxwell model. So both these Kelvin-Weigelt and the Maxwell models are derived from these models. So they are the simple viscoelastic models which are derived from these particular models. Apart from this linear viscoelastic models, we also have the non-linear viscoelastic models. So the one discussed in the lecture is the Pantane Tanner model. So that usually describes the flow behavior or the material behavior under under large deformation in non-linear conditions. So this is something which will be useful for polymer processing. So this is still here about the models for describing the rheological property rheology of the polymers. So if you have any doubts, you can ask me. Apart from that, we have to discuss about swelling, after which we will start our session on solving problems. So some of the some of the questions we have to discuss. So before that, if you have any doubts, you are welcome to ask me. So let's start our discussion on swelling of polymers. Since I think there are no doubts related to the part that we discussed right now, let's start our next discussion on swelling in polymers. So polymers typically have the tendency to swell in solvents. So what happens is when you place certain polymers, not all, certain polymers, what actually happens is these polymers actually absorb the solvent and they increase in volume, and that phenomenon is called as the swelling in polymers. So what actually happens is, so since polymers are of from their structures, if you see the physical structures, since polymers are different from one another, so we have the classification of polymers as linear polymer, branch polymer, or highly branched and cross-linked polymers, right? So this is what we discussed in week 1, so where we discussed about different types of polymers. We also, so based on, so one of the classification was based on their structure, not the chemical one, but how they are arranged, or how the molecule, you can say how the monomers are connected to each other. So what happens is, in case of linear and branched polymer, so when you actually place this type of polymers in the solvents, two types of phenomenons can happen. So one is the plasticization and another one is called as the solubilization. So plasticization is a phenomena where the solvent molecules in which you actually place your polymer, that solvent molecule can act as a plasticizer and can interact with that polymer and increase the segmental flexibility of the polymer chain. So already there is a polymer chain which has certain amount of conformational disorderness. So because of this solvent molecules, what happens is they act as a plasticizer and they increase the segmental flexibility in this polymer chain. The second case is called as the solubilization, where what actually happens is there is so much amount of solvent that is going to be present around the polymer that the polymers actually start separating and they dissolve in the solvent. So these two phenomena are something that is typically observed in case of linear or branched polymers. So here what I want to ask is, I said plasticization actually helps in the plasticizer increases the segmental flexibility of the polymer chain. But how do you quantify this? Or you can say, or let me also put it in another way. So the polymers increases the the solvent molecules increases the segmental flexibility of the polymer chain. So this is typically identified through DSC characterization technique, differential scanning calorimetry that we discussed in the previous live interaction session. So my question is, what is observed in case of DSC which helps us to know that this solvent plasticize or act as a plasticizer for the polymer? How do we actually convey, or how does the DSC convey this message to us that the segmental flexibility of the polymer chain is increased? We discussed about this in the previous sessions as well. Anyone? How does DSC convey us this, or You can put it that way itself. How does the DSC conveys us that a particular polymer chain, or you can say a particular polymer which is soaked in a solvent, or you can say placed in a solvent, its segmental flexibility has been enhanced. How can we interpret? I mean, I'm saying, this is fine that solvent molecules act as plasticizer and increases the segmental flexibility or segmental mobility of the polymer chain. But how do you actually, how the DSC machine DSC characterization technique conveys this message? So, can we detect that possibly using glass transition temperature? TG. So depending upon the value of Tg, can we say a particular polymer that we are taking is plasticized, and does that mean decrease in the glass transition temperature? Does it indicates that your polymer is plasticized, or you can say that the segmental mobility or flexibility is enhanced? Any response on this? So I'm going to write it down here. A decrease in, sorry, just a second. TG indicates enhanced segmental flexibility in polymer chains. So let me know about this. Let me progress further. Think about this. So these two phenomena of plasticization and solubilization happens in case of branched or linear polymers. However, when you go for the cross-linked polymers, or called as thermosets and rubbers, what actually happens is they have cross-links in them. So those crosslinks are typically covalent in nature. They are covalently bonded to one another. Those crosslinks, what you see, there is the presence of covalent bond in those crosslinks. So even if you put this polymers in case of the excess of the solvent, they are not going to break down or separate, unlike in case of your linear or branched polymers. So that is where the concept of swelling comes in. So when you put this kind of polymers, or the cross-linked network polymers, inside a solvent, what actually happens is there is an influx of the solvent into the polymers, and then because of the influx of the solvent, the polymer is going to swell, it is going to increase in its volume. How this happens is, once there is an influx of the solvent, the polymer chain is going to stretch because of its segmental flexibility it has, and the polymer molecules are going to move apart, providing space for the solvent to be inside that structure. But again, it has its own capability, right? It cannot swell the entire amount of solvent that you actually add to the polymer, or it cannot absorb the entire solvent in which you actually place the polymer. So, how much can a polymer swell? Or what are the parameters that usually decide how much amount of the water can, or how much amount of the solvent can enter inside a particular polymer or a polymer matrix? So, that typically depends upon two factors. One is your osmotic pressure. So, the solvent usually enters into the polymer, which is usually affected by the osmotic pressure, and then there is another opposing factor, which is your chain elasticity. So what happens is, as the solvent enters, the polymer molecules are going to be stretched, and this actually creates a internal stress inside the polymer. So because once the polymer is going to be stretched, what happens is, this is something that we discussed previously also. If a polymer is going to be in a coiled state, the conformational disorderness is going to be more. However, when the polymer is stretched, or it's going to go inside an expanded coil state, or it's going to be stretched, what happens is the conformational disorderness decreases. Since the conformational disorderness decreases, the conformational entropy is also going to decrease. And this we have learned before itself. So based on that, if the polymer chain is going to stretch, what actually happens is an internal stress actually gets generated, which actually limits the amount of solvent that enters inside the polymer, and that actually prevents the swelling. So usually the equilibrium is typically reached between this osmotic pressure as well as that of the stress that gets generated inside the polymer matrix. Apart from that, the swelling also depends upon the density of the cross linking. So, can anyone make a, or can anyone tell how does the density of the cross linking affect the swelling ability? I mean, is it directly proportional, or is it going to be an inverse relationship? It's going to be an inverse relationship, because more the cross links, swelling will be less, because more the cross links, the chains between the polymer chains between each of these cross links is going to be shorter. So since shorter means the polymer chains are going to resist stretching more quickly, so since they resist stretching, the solvent molecules cannot come inside, so that means swelling ability decreases. So so swelling will be less in those cases. So higher the density of cross-linking, lower will be the swelling ability. Again, another thing, factor that affects the swelling ability is going to be their polymer solvent interaction parameter. More negative than the value of psi, which actually quantifies the polymer solvent interaction behavior, higher will be the swelling of the polymer. So this is about swelling of the polymer, and if you ask where does this have a role, so usually this has a more roles in case of materials like hydrogels, organogels, and in case of smart polymer devices. So basically this is a kind of a concept, that is a concept which is of a great interest in the scientific domain. The use of polymers for electronic devices, specifically wearable electronic devices. So when you have to have a device which is going to be compatible with your human skin, then the swelling of the polymers is going to be an important factor under consideration. because the polymer that you're going to use for a wearable electronic devices should be compatible with your skin. So they should have certain amount of swellability and water content in their structure so that they can interface with the biological tissues. So that is a place where the swelling of the polymer holds important holds importance. So this is about the swelling. So this ends the discussion here. If you have any questions, you are welcome to ask me now, or else we can progress for discussing some of the problems that we have for today's live interaction session. So meanwhile, let me read out this question. If you have any doubts related to what we have discussed right now, you are welcome to ask. So, for a polymer solution, the dependence of viscosity on shear rate is described by a three parameter Carreau model given by eta equals to eta naught 1 plus delta times shear rate the whole square and whole power n minus 1 by 2. So here if you see the high shear viscosity that we have discussed previously in case of the Carreau model is going to be 0. So that typically reduces to the cross model, or also you can say it as a three parameter Carreau model where eta naught uh, sorry where eta naught n and gamma are the three parameters of the model. Here all three parameters are going to be positive. As the shear rate increases from 1 second, or you can say 1 to 100 per second, the viscosity of the polymer solution decreases by a factor of 10. For a polymer solution with n value as zero point 0.4 and eta naught as 15 pascal second, calculate the value of the lambda parameter. So this is the three parameter model, eta naught, lambda, n. Now we are given with the value of eta naught, n. We are asked to calculate the value of lambda. What else we are given is nothing but is the what else we are given with is the three parameter model, that relationship, and also information that the shear rate increases from 1 to 100. Then the viscosity of the polymer solution decreases by a factor of 10. So based on this information that is available, we are supposed to calculate the value of lambda. That is nothing but it's going to be a characteristic time, or you can also call that as time constant, to see how quickly the fluid's viscosity is actually going to move from the zero shear plateau to power law region. Anyone with an answer? I think this. So here you need what you need actually need to know is the how to use this relation. That is, if your shear rate is going to increase by a factor of 100, viscosity is going to decrease by a factor of 10. Based on this information, you need to substitute the value of eta naught and n, and then you are going to calculate. You will be able to calculate the value of lambda. So let us start solving. Okay. So I'll going to directly take this relationship from here and paste it. So this is what we have it in our question. So let this be the equation when the shear rate is 1 second inverse. So in that case, even the shear rate is going to be 1 second inverse, this is just going to be lambda square. This will be the equation when shear rate is 100 second inverse. So then the equation will change. So I have to substitute the value of gamma dot as 100. So that will be 100 lambda square. So let me represent this as eta dash. So if you divide these two equations, then you will be able to solve for the value of lambda. So let's divide equation 1 by 2. So then it's going to be just a second. Eta by eta dash is going to be eta naught is going to, since eta naught value is going to remain same, so that we don't need, so that will get cancelled out. So this will be 1 plus lambda square by 1 plus, so 100 square will be 10 power 4, so the entire whole power n minus 1 by 2, n value is 0.4, 0.4 minus 1 is minus zero point 0.6, by 2 is minus zero point 0.3. So eta by eta dash, it says that as the shear rate is increased, the value of viscosity it decreases by a factor of 10. So eta dash is going to be eta by 10. So that means eta by eta dash is going to be 10. Or you can say eta is nothing but, or eta dash is zero point 0.1 times eta, or eta is 10 times eta dash. So eta by eta dash is going to be 10. So 10 by, whole power zero point 0.3. So I have just inverted the sign because we are bringing it from numerator to, so we are just switching the numerator and denominator, so that is the reason I have changed the sign from minus zero point 0.3 to plus zero point 0.3. So 10 to the power 1 by zero point 0.3 is nothing but, so 10 power 1 by zero point 0.3. Let us use the calculator. So 10 power 3.33 is going to be 2154.43. This is going to be, so this times 1 plus lambda square is equal to 1 plus 10,000 times lambda square. So now if you do the mathematics, then you are supposed to get 2153.433 equals to, sorry, 10,000 minus 2154.433 times lambda square. Just a second. So if you do the, Just a second. Let me use my personal calculator to get the value. So lambda square is going to be equal to 0.2744. So that means lambda value is square root of 0.2744, which is nothing but 0.523. So this is going to be the value of the time constant. And what will be the units? Seconds. So that will be the unit. So the value of lambda is 0.523 seconds. So let me know whether you are also getting the same value. I hope the calculations are fine. Any doubts with respect to, or any different answers with respect to what I have got, what I have calculated here? If not, I think we can move towards next few questions. So if you have any doubts, please let me know, or else we can move forward. So these are few of the MCQ, I mean multi-choice questions, theoretical ones, and I hope this should not be difficult. So the question is, Carreau Yasuda model is used most often to describe, is it the yield stress of the polymer melt, or is it the shear thinning polymer melt, constant viscosity polymer melt, or the normal stress difference of polymer melt? I think this should be easy. We have discussed this just a few couple of minutes back. So anyone? This is basically what is the use of the model. So it's used to describe the shear thinning of the polymer melt. But if that is so, Carreau Yashoda model is used to describe about the shear thinning of the polymer melt. If that is the case, what about the other cases? Yield stress of the polymer melt is described by what model? Constant viscosity is described by what model? And in which type of model does the normal stress differences describe? So you look at those and then let us discuss this question in the next class, because apart from knowing answer we should also know for what other or what other options are there and what they are, what they actually represent. So apart from knowing the right answers we should also know about the other options in the question. So please look at this question. Then next question, this should be very easy one. The term eta naught in Carreau model refers to intrinsic viscosity, zero shear viscosity, inherent viscosity, and or reduced viscosity. Anyone? So as we discussed, eta naught represents for zero shear viscosity, that is the constant viscosity at zero shear rate, and eta infinity represents for the infinite viscosity, that is your viscosity at a higher shear rate. And I hope you guys, everyone is able to remember about the other intrinsic viscosity, inherent viscosity, and reduced viscosity, what we discussed when discussing about the concept of just a second, about the concept of Mark-Howing equation. So I hope you guys are able to remember that. So if not, please look at those presentations or the recorded lectures which are available in the YouTube. So with respect, next question is, with respect to response of polymer solution according to the Carreau Yasuda model, shear rate at which the onset of the shear thinning is observed is related to the largest relaxation time of the material. True or false? If and justify. Anyone? Is it true or is it false? It's going to be true. Yes. Am I correct or am I wrong? Or eh, you require time to think about this question? Hmm. Okay, so you are saying you require time. Okay. So since one of you have just responded back that you require time to think about this, so let's discuss this in the next class. Let's go to this. Flory Rehner equation uses network elasticity, where swelling leads to stretching of segments and dash in entropy. Increase, decrease, constant, and zero. So, again, if you just see the sentence, you can actually come up with the answer. Flory-Rehner equation uses network elasticity. Swelling leads to stretching of segments, and how does it affect the entropy of a system? We just now discussed a very few minutes back, 10 minutes back, if I'm not wrong. It's related to the conformational disorderness of a system. So, as we discussed in a coil state, the polymers, the conformational disorderness is going to be more. So, when the polymer moves, or you can say, yeah, you can say moves from coil state to expanded coil state to when they are stretched, so the conformational disorderness is going to decrease. So entropy is a measure of the degree of the disorderness, conformational entropy. So as the degree of the disorder conformational disorderness is going to decrease, entropy also is going to decrease. So is it that the option is B? Is it fine? This we just now discussed. Swelling leads to stretching of the segments, move the polymers apart so that the solvent molecules can occupy that particular space between the polymer chains. And since the polymer chains are going to get stretched, they are actually the disorderness is going to decrease, so entropy is also going to decrease. So it will decrease, entropy will decrease. So before we close our session for today, since we have already almost reached our time limit, let's look at this question. Given the weight of dry polymer network is 0.68 and weight of swollen polymer network is 1.2, what is the swelling ratio? It should be a easy one. Swelling ratio. That is what we are asking is how much weight of the solvent is inside the polymer network, is inside the polymer system, you can say, inside the swollen polymer networks. So it's just going to be a mere, so swollen polymer network's weight, if you subtract that with the dry polymer network weight, you're going to get the value or the amount of solvent that is present in the swollen polymer network. That if you divide with the dry polymer network's weight, will you be able to get what is the swelling ratio? So sorry, so will can the answer be 1.2 minus 0.68 by 0.68? Again, since they have asked based on the weight, I am going to not multiply with 1000 with 100 for percentage. So what will be that? 0.52 by 0.68, so something less than 100%. So this is how you calculate the swelling ratio of the polymer networks, or you can say the swelling ratio is calculated through this way. So if you have any doubts, you are welcome to ask me before we conclude our session for today. Anyone with any queries or doubts? Anyone? So let me stop sharing. So if you have no doubts, and then I think we can conclude our session for today. So I thank everyone for joining today's live interaction session. Our last live interaction session will be on 12th October 2025 from 5 p.m. to 7 p.m. I thank Professor Abhijit Deshpande sir as well as the NPTEL team for providing me this opportunity to interact with you all on this Sunday afternoon. So if you have any doubts, you're also welcome to email me. My email ID will be available in the presentation that will be uploaded in the coming week. So thank you everyone for joining today's live interaction session. Have a great weekend and a happy week ahead. Thank you and bye.